Hello, Honors Chemistry, and welcome to Chapter 7, Sections 7.3 and 7.4, where we talk a little bit about the art of balancing chemical equations. Now, this should really be a review from 8th grade, right, because you guys have done this already. So this should be quick and simple. Now, if you did not do a lot of practice with balancing chemical equations in middle school and you are struggling here, then make sure you talk to me sooner than later so we can make sure that we help you get enough practice to master this, okay? All right, so for starters, balancing chemical equations. Why do we have to balance a chemical equation? Right, it goes back to the law of conservation of mass, yes? Right, in that however many atoms of oxygen are on one side of the reaction, there must be a matching number of atoms on the other side of the reaction, right? Because that's how life works, right? We cannot create oxygen out of nothing. We cannot destroy oxygen during the process. So it's got to balance out. But we're also restricted by the fact that methane, for example, so this is methane, this is natural gas, right? Methane comes as a molecule of CH4, right? It's always a carbon bonded to 4 oxygens. That simply is the structure of methane, right? Which means that even though when I produce water, water only has 2 oxygens, right? Because we know that water is always 1 oxygen bonded to 2 hydrogens, right? And from middle school, I feel like you should kind of be familiar with that, right? But that's always what water looks like, right? So if I have 4 hydrogens in every 1 methane and every water only has 2 hydrogens, right? I have to find some other way to make that work, right? And that's where the balancing comes in. That's where the concept of coefficients comes in, okay? In that I can have more than 1 water molecule. If I had 2 of these, now I have 4 hydrogens. Yes, does that make sense, right? And as a point of reference, right, if we look at oxygen, right, oxygen always comes as a molecule of O2, right? That's the only way oxygen appears in nature is O2, a diatomic molecule, right? But we know, right, from chemical analyses that carbon dioxide is produced, and carbon dioxide is always CO2, right? And so again, we have to make sure everything balances to obey the law of conservation of mass, right? We cannot ever change these subscripts because the subscripts are determined by the chemical makeup, right, of the atoms combining, right? What are their charges? What are the distribution of electrons? How can they share them, etc.? You will never ever change the subscripts when you write or when you balance a chemical equation, right? Balancing is always going to be about coefficients. All right. Final tidbit on this page, right? Our states, right? So you'll see that, all these layers of color because I scribbled all over it already, right? We have G's here, right? All those G's stand for, yep, you guessed it, gases, right? And so there are just certain things that are gases. So we'll assume that most of these are at room temperature unless we say otherwise, right? And so if we think about the things that are gases at room temperature, things that you should know are gases, for example, right? We have our H2, N2, O2, Cl2, F2, right? And obviously there's like carbon dioxide, which I feel like you should know. These things are all gases at room temperature, which means that when you're writing an equation, they will get that G next to them to indicate that they are gases, right? And obviously there are exceptions, right? Because here in this case, we might assume that water would fall under liquids, right? That seems to make sense. Water is a liquid at room temperature, right? But if we're thinking about a combustion reaction, right? If you think about your stove at home, for example, or if you've ever had if you work the grill at home, right? Are there puddles of water when you're done? No, there are not, right? Which tells you, right, that in this case, that emission of heat, lots of heat for that matter, right, makes the water gaseous as we produce it, right? So just as a tidbit to tuck away, right, when you're writing combustion, water is more often than not present as a gas on the product side, right? But in general, at room temperature, right, so at room temperature, water will be a liquid, right? In terms of elements, right, you should know that bromine is a liquid, right? And obviously mercury is also a liquid at room temperature, right? Which means that everything else on the periodic table is a solid. So all other elements are solids at room temp, right? In addition, ionic compounds are solids at room temp. Okay, then that leaves us with the one that is a little bit weird and different, right? Which are our aqueous labels, right? So aqueous labels are, like it says in your book, right, for aqueous solutions, right? And when we think of a solution, specifically, that means something dissolved in water, right? So in order for it to get an AQ label, one, there has to be water present, and two, it must be soluble in the water. And so, right, so obviously there are a couple of things that you should, like sugar, you know sugar is soluble in water, right? That's a life thing you should know, right? Other than that, we would use our solubility rules to determine that, which will, oh my gosh, come up in just a few sections. So anyway, we will revisit this when we get there. All right, now let's go back to balancing. So this is what we just talked about on the other page, right? CH4 is always CH4, right? But H2O is always H2O. So how do we do that, right? We use coefficients to balance our equation, right? Because in the end, right, the total number of atoms on the reactant side must equal the total number of atoms on the product side, which means that the total mass is equal to the total mass. Yes, before and after. Yes? Does that make sense, right? Okay. So then let's go ahead and do a few practice problems. So it says that we have solid chromium 3 oxide and solid carbon produce chromium and carbon dioxide. So first, obviously, we have to use our skills that we've acquired since chapter 5 to put these formulas together, right? So remember that this applies to that, right? So we have Cr3 plus. Oxide means this is oxygen, which has a 2 minus, right? So it means we have Cr2O3 solid, right? Plus solid carbon to produce chromium. And now chromium is an element that is not one of these gases or one of these liquids, which means it's a solid, right? And it's a metal. I feel like, you know, those are things we should be kind of sure about. And CO2 gas, right? So now we just need to balance using coefficients, right? So first pass is all about writing the formulas correctly based on chapter 5, right? Based on charges, based on prefixes, based on elements that we've learned from the periodic table. And then we will go back and balance using coefficients to make sure that the total number of atoms on one side of each type are on the other side also, right? So let's go ahead and do that. And obviously, like your book recommends, right, I also recommend that you would save the elemental things for last, right? That would be the easiest, right? So carbon we might save for last. Chromium we'll save for last. But we do see here, right, there's an oxygen here and an oxygen here. So let's make those match, right, because those are both stuck in a compound. We have 3 on one side, and we have 2 on the other side, right? So really all we're doing, this is like fractions again, right? We're looking for the lowest common multiple between 3 and 2, which is 6, right? So if I put a 2 out here and a 3 here, now I have 6 oxygens on each side, right? This also means I have a total of how many chromiums? 4, right? So I'll fix that there. I also have a total of how many carbons? 3, right? And then so we'll go back and double check, right? I have 2 times 2 is 4 chromiums. I have 2 times 3 is 6 oxygens. 3 times 2 is 6. 3 carbons, 3 carbons. Okay, we're done. Yes? Okay, so next up we have gaseous this, which is butane gas, plus oxygen, life things you should know. You should just know that that's diatomic and a gas. Carbon dioxide gas, water, which I just told you, if we have a combustion reaction, typically a gas, right? And we're going to clarify towards the end of the unit, right, the end of the chapter, right, that a carbon-hydrogen compound plus oxygen is combustion. So we've written all the formulas based on stuff from chapter 5, right? We've used our prefixes, we've used our knowledge of elements. Now we'll go back and add coefficients, right? So we'll save the oxygen for last and we'll balance everybody else first, right? So here are 4 carbons, here's 1 carbon, right? So we'll go ahead and put a 4 here, right? We have 10 hydrogens here and 2 hydrogens here, so that means we'll have to put a 5 here, right? And then when we do that, let's check our oxygens now, right? So we have 4 times 2, which is 8. We have 5 times 1, which is 5, which gives us a total of 13 oxygens, right? Here we have 2. So here you have a couple of options depending on what works for you, right? Your book would recommend that you go ahead and take 13 over 2, right? Because that's what you need. And then you would take this whole thing and multiply it by 2. And that would give you your correct coefficients. Because obviously we're not going to leave a fractional coefficient in here, right? But 13 over 2 is what's going to give you the right number of oxygens, 13, right? Because this is O2, okay? And then we would multiply that 2 through, right? And we would get a 2 here, a 13 here, 8 here, and 10 here for coefficients, right? Alternatively, once you understand that there is, not everybody likes having to deal with fractions, right? Fractions don't work for everybody. Once you understand that you have an odd number of oxygens, right, 13 here, then what you have is an odds and evens problem, right? And so you just need to fix the thing that makes it odd, right? And the thing that makes it odd, if we pay attention, right, is this hydrogen over here, right? The fact that we had to put a 5 in front of that hydrogen. So let's go back and change that. Erase all of our coefficients. Now, that 5 came from here. So change the coefficient there, yes? Now we put a 2 there. Let's go back and try again. Now I have 8 carbons. Now I will put a 10 here, which means that now I have 8 times 2, which is 16, plus 10, which gives me 26 oxygens, which means I'll put a 13 here. So you see that we end up in the same place. You just don't have to deal with fractions. You just deal with the odds and evens. You should do whatever you feel works best for you, okay? Next up, some more practice, right? Lead 2, right? So this is Pb2 plus acetate, C2H3O2 minus, right? So that means we have Pb, C2H3O2, 2, and it's aqueous, it says, right? Plus aqueous potassium iodide, right? So potassium iodide, right? Which means it's the binary aqueous, right? Forms solid lead 2 iodide. So again, Pb, that 2 goes to that lead, so that's Pb2 plus and I minus, so PbI2 solid plus potassium acetate aqueous, okay? And now, again, we'll go through and we'll balance with some coefficients, right? So here, it looks huge, right? But the thing to remember is that anytime a polyatomic ion stays the same polyatomic ion on both the reactant and product side, you'll balance it as its own entity, right? So I'm not going to go through and balance carbons, hydrogens, and oxygens separately. I'm going to balance acetates, right? So I have 2 acetates on this side, 1 acetate on that side, so I'm going to put a 2 here, yes? Which means that now I have 2 potassiums, so I'm going to put a 2 here to fix that. Oh, lo and behold, that gives me 2 iodides, which, I already have 2 iodides there, right? We're good to go. Yes, does that make sense, right? If you prefer, you can balance them piecewise, right? But as long as a polyatomic ion stays the same on both sides, I would choose to balance it as its own entity. Next up, we have our last reaction where we are given this, so we're just going to go ahead and balance that, right? So we will save the oxygen and the chlorine for last. We have these hydrogens that are hanging out in compounds. So if I have 2 here, I'm going to go ahead and put a 2 here, which is going to give me 2 chlorines and then 2 chlorines, right? Oh, but then there are those oxygens. And so here, right, what I would do is I would see that there are 2 oxygens here, 1 here. That doesn't work, right? So I'm going to have to put a coefficient in front of water. So for me, I would just go back and erase that. And I will start by putting a 2 here now, right? And that 2 now means I have 4 hydrogens, which means I now have 4 chlorines. And then we're done. Yes, does that make sense? Odds and evens. All right, thank you for listening. Be good, and I will see you soon.